We usually think of light as the fastest thing in the universe, racing through space at nearly 300,000 kilometers per second. So the idea of slowing light down sounds paradoxical, almost like trying to delay a lightning bolt. But remarkably, in the right conditions, light can indeed be slowed dramatically, down to walking speed, or even brought to a temporary halt. This phenomenon, known as slow light, has been observed not only in exotic materials like Bose-Einstein condensates, but also in engineered systems like optical fibers and photonic crystals. But how is this possible? And what does it mean to slow down a photon? To understand slow light, we must distinguish between two different velocities. The phase velocity, which is how fast individual wavefronts move, and the group velocity, which is the speed at which a pulse of light carrying information or energy travels. Slow light refers to reducing the group velocity of light, often through manipulation of the refractive index and dispersion properties of the medium through which light travels. In certain cleverly designed materials, the group velocity can be reduced by many orders of magnitude, allowing a pulse of light to be stretched out in time and space. How is it done in optical fibers? In traditional glass optical fibers, light travels slightly slower than in a vacuum due to the refractive index, now 1.5, but to make light really slow, by factors of 10, 100, or more, researchers use techniques like electromagnetically induced transparency. Originally demonstrated in atomic vapors, EAT uses a control laser to open a narrow transmission window in an otherwise opaque medium. The refractive index changes rapidly in that window, producing extreme dispersion that slows the group velocity to a crawl. Variants of this technique have been explored in doped fiber systems and waveguides, stimulated Brillouin scattering. In optical fibers, a laser beam can generate acoustic phonons, vibrations in the fiber material. These phonons interact with a second light beam to produce a backscattered signal that effectively carries a memory of the pulse, delaying it by nanoseconds to microseconds. SBS-based slow light systems are practical and have been demonstrated in commercial fiber lengths. Photonic crystal fibers. These are fibers with a periodic microstructured cross-section that allows extreme control over light propagation. By tailoring the dispersion characteristics, researchers can engineer waveguides where the group velocity is slowed by designing narrow-band resonances that cause light pulses to linger. What is actually happening to the photons? Photons are never truly slowed in the sense of changing their inherent speed, which remains c in vacuum. Instead, what slows down is the information C-carrying pulse, a group of photons whose collective behavior is modified by the medium's response. The photons are constantly being absorbed and re-emitted or scattered in ways that make the pulse take longer to traverse a given distance. In a way, photons in these media behave a bit like a team of runners passing batons. The baton moves slowly across the track, even though each runner, photon, runs at full speed between handoffs. Why does slow light matter? Slowing light down has several promising applications. Optical buffering. Delaying light pulses is useful for synchronizing signals in telecommunications without needing to convert optical signals back into electronic ones. Quantum information storage. In quantum optics, the ability to slow or store light pulses, especially single photons, is vital for quantum memory and quantum repeaters in long-distance entanglement networks. Enhanced nonlinear interactions. Slower light interacts with matter more strongly, making it easier to achieve nonlinear effects like frequency conversion or photon interactions, even at low intensities. Sensors and gyroscopes. The enhanced interaction time between light and matter increases the sensitivity of certain interferometric sensors, including those used in navigation and geophysics. Can light be stopped completely? Yes, in a sense. Using EIT and ultracold atomic gases, researchers at Harvard and MIT in the early 2000s managed to halt a light pulse entirely by converting it into a collective excitation in the atomic medium, then later retrieving it as a photon pulse. This light storage was a landmark in quantum optics, showing that photonic information can be parked, stored, and retrieved in material systems. Final paradox: is light still light when it slows? This raises a subtle philosophical question. Is a photon in slow light still a free particle of light, or does it become a hybrid quasi-particle, part light, part matter? In many systems, especially those involving strong coupling between light and atomic states, The photon effectively becomes a polaritonic excitation, a blend of electromagnetic wave. In the end, slow light reminds us that photons are not just packets of energy zooming through the void. Their behavior is shaped by the medium they move through and by our ingenuity in designing that medium. Just as Einstein showed that time and space are not absolute, modern optics shows that even light's speed can be a matter of context. Slow light refers to techniques that reduce the group velocity of light pulses to a fraction of their normal speed in vacuum, c3 x 10 to the power of 8/s. In optical fibers, this is achieved by engineering the fiber's refractive index profile or exploiting dispersion and nonlinearity to create conditions where different frequency components interfere and delay the pulse. Methods such as stimulated Brillouin scattering at SBS, electromagnetically induced transparency in doped fibers, and photonic crystal fiber designs can achieve delays of nanoseconds to microseconds over meter-scale lengths. By coupling pump and signal beams or tailoring microstructure, one can dynamically tune the delay without converting photons to matter excitations. Maintaining pulse fidelity requires careful management of dispersion-induced distortion and absorption loss. Such controlled delays enable buffering, synchronization, and enhanced light-matter interactions in fiber-based systems. Using SBS in standard silica fiber, researchers have demonstrated tunable delays of up to 40 ns over a 20 m fiber span by adjusting. Stimulated Brillouin scattering occurs when an intense pump light generates acoustic phonons in the fiber, creating a moving density grating that scatters a counter-propagating signal. The signal light is amplified by energy transfer from the pump and emerges delayed relative to its arrival time if tuned to the Brillouin frequency shift. The delay is proportional to pump power and interaction length, but limited by phonon lifetime, (10 in silica. Achievable delays of tens of nanoseconds are practical in telecommunications fibers with modest pump powers, (100 at P). However, increased pump intensities raise noise and can induce nonlinear distortions. Engineering specialty fibers with higher Brillouin gain can enhance delay without excessive pump requirements. A 1 TM highly nonlinear fiber produced a 200 m's delay at 1550 m using a 200 MW pump. It's like pushing on a crowd wave in a stadium. Stronger pushes sustain the wave longer and slow its propagation speed. P in optical fibers uses resonant interactions in doped fiber sections, e.g. erbium or praseodymium, where a control beam opens a narrow transmission window within an absorption line. Inside this transparency window, the group index skyrockets, slowing light by factors of 10 to the power 3 to 10 to the power 6. Achieving EAT requires precise control of pump frequency, polarization, and temperature to match the dopant's 3-level atomic system, despite causing minimal absorption. EIT-based delays suffer from limited bandwidth, M009, and require cryogenic cooling for some dopants. Room temperature implementations in hollow core photonic band gap fibers filled with atomic vapors are emerging to relax these constraints. Such setups promise integrated slow light buffers compatible with quantum memory applications. Praseodymium doped fiber demonstrated 5 US delay of a 200 meter bandwidth pulse at 606 mm, under 4K cooling. It's like opening a single narrow gate in a dam. Water passes, but is forced to trickle slowly through that constriction. Photonic crystal fibers, PCFs, incorporate periodic air hole arrays in their cladding, allowing precise dispersion engineering to create flat, anomalous dispersion regions. By tailoring the hole size and pitch, PCFs can support slow light propagation via dispersion-induced pulse stretching. Unlike SBS or EIT, PCF delays are passive and broadband seconds over tens of centimeters. Combining PCFs with chirped Bragg gratings further enhances delay and storage time without significant losses. Such fiber structures can be fabricated using stack and draw methods, making them compatible with existing fiber networks. Applications include ultrafast signal processing and optical coherence tomography. A 30 SCM PCF with engineered dispersion achieved a 2 n's delay for a 50C pulse at 1550 m. It's like designing a winding mountain road instead of a straight highway. Vehicles still traverse the same distance, but take longer due to extra curves. Coherent population oscillation, CPO, in doped fibers creates a slow light effect by saturating absorption transitions with a modulated pump, inducing a narrow spectral hole and steep dispersion. The resulting group index can reach values of 10 to the power of 4, delaying pulses by microseconds in centimeter scale fiber sections. CPO operates at room temperature and does not require acoustic phonons, distinguishing it from SBS. However, the narrow spectral hole limits usable bandwidth to MX scales, making CPO suitable for narrow band signal processing and sensing. Optimizing dopant concentration and pump intensity balances delay versus distortion. Integration into fiber Bragg grading platforms enhances practical deployment. An erbium-doped fiber exhibited a 1US delay of a 10-minute modulation through CPO at 1530. It's like creating a temporary toll booth that modulates car speed, letting vehicles through slowly while the booth operator oscillates open and closed. All slow light methods face inherent trade-offs among delay, bandwidth, and attenuation. Larger delays typically narrow the transmission bandwidth, causing pulse distortion and information loss. Scattering, absorption, and nonlinear effects accumulate over the interaction length, reducing signal-to-noise ratio. Practical devices therefore optimize for a target application. Long delays for narrowband signals, e.g., quantum memory, or moderate delays for broadband telecom pulses. Temperature fluctuations and environmental perturbations can shift resonance conditions, requiring active stabilization. Ongoing research seeks materials and structures with high delay bandwidth products and low loss. A 20-inch SBS-based buffer had a usable bandwidth of only 100 MHz before significant waveform distortion occurred, like using a narrow culvert to delay floodwater. You can hold back a lot of water, but only if it trickles through a small hole at a time. Modern systems incorporate dynamic pump modulation, temperature tuning, and strain control to adjust delay on the fly. In SBS buffers, varying pump power linearly tunes the delay over tens of nanoseconds in real time. In PCFs and fiber gratings, applying strain or heating elements shifts dispersion characteristics to match varying signal requirements. EIT and CPO-based modules integrate electronic feedback loops to lock pump frequencies to resonance conditions despite drift. Such reconfigurability enables adaptive optical networks, ultrafast computing elements, and tunable delay lines for phase surplus sensors. Real-world demonstrations include dynamically synchronizing data streams over fiber links without electronic conversion. A reconfigurable SBS delay module adjusted delays between 5 and 50 ends within modulating pump intensity. It's like adjusting the timing on traffic lights in response to real-time congestion, keeping vehicles flowing smoothly despite changing conditions. Slow light buffers can temporarily store optical packets in all optical networks, reducing reliance on electronic memory and increasing data throughput. In quantum communication, controlled delays enable synchronization of single photon qubits for interference-based protocols and quantum repeaters. Dispersion-engineered fibers support low-loss delays compatible with entangled photon pairs. Slow light also enhances light-matter interactions for nonlinear optics, improving wavelength conversion and optical switching efficiency. Integration into planar waveguides and photonic chips points toward compact, scalable devices for next-generation networks. An SBS-based buffer demonstrated error-free storage and retrieval of 10 GB/s optical pulses in a live fiber link testbed. It's like using a holding pen at a loading dock, letting trucks wait in line until the warehouse is ready. Except here the trucks are light pulses carrying data. The ultimate goal is to achieve on-demand light storage, slowing pulses to zero group velocity and then re-releasing them without distortion. Hybrid approaches combining atomic vapor cores with hollow core photonic bandgap fibers show promise for room temperature, long lifetime quantum memories. Nanophotonic resonators and metamaterials offer sub-wavelength confinement and giant dispersion, pushing delays into microsecond and millisecond regimes in chip-scale devices. Theoretical advances in topological photonics suggest robust slow light modes immune to scattering losses. Realizing stopped light would revolutionize optical computing, memory, and sensing, enabling truly all-optical data centers. Researchers stored an optical pulse in a cold atom ensemble coupled to a hollow core fiber for 1 EMS before retrieving it with 70% efficiency. It's like catching and holding a soap bubble in midair, preserving its shape indefinitely until you choose to let it go.